So when you think of parallel, it's more to do with gradient, but we can't really have the idea of gradient when we're dealing in 3 dimensions, okay? It's not really a concept that exists, but we can do something similar, and we often want to prove that they are parallel, or at least they're kind of running in the same direction. And we do that by using this idea of scalars, okay? So we know that for some scalar k, ku is parallel to u, okay? So that's what we looked at before. If we had the vector u, and we had the vector 3u, it's basically just 3 u's back to back. They're still parallel, okay? So that can help us prove, not that they're got the same gradient, but they're in line with each other. We're going to use that quite a lot in the topic that's coming up, okay? So just a kind of recap of what we did before, if I had the vector AB, which is 3, 2, 1, 2AB would be 2 ABs back to back, or what we call tip to tail, okay? And in which case it would just be another vector that's 3, 2, 1 put on the end, in which case the whole thing would be 6, 4, 2, okay? In which case the vector AB and the vector 2AB are parallel to one another, okay? And we're going to use that concept to help us in the next stage. Oh, not quite. I'm getting there. So if we have a vector like this, if ku is instead just a new vector v, we can say that u and v are parallel. You might see this symbol from time to time. Okay, it's u and v, obviously, with 2 lines in between. And those 2 lines in between basically tell you that the vectors u and the vector v are parallel with one another, okay? So if u and v are parallel, then there exists a scalar k such that u equals kv. And basically what that means is there's a number that you can multiply each vector by in order to give you the components of the other vector, okay? Don't worry too much about the whole idea of scalar. Scalar is just a number, okay? But the idea is that, as I say, if you took a number and you times it by u, okay, a certain number, then you would get v. And likewise, you can do the same in reverse, okay? So if u equals kv for some scalar k that doesn't equal 0, so this is the only thing we've got to be careful of, is that it can't equal 0, then u and v are parallel. So it's just the vice versa, just the kind of the opposite of what we said before, but both of these things allow us to prove something in the next example, okay? So if the vectors u and v are parallel, calculate the values of a and c. So what this is telling us is that there is some scalar, some number k, okay, that exists, that when we multiply one of these vectors by that number, we will get the other vector. So what we're looking at here is, because a and c are both in this vector, the only thing that we can use to connect them are the 6 and the 2. Okay, because we're told that they're parallel, we know that we've multiplied one of these vectors by this number k to give us the other vector, okay? So as long as k doesn't equal 0, then a6c will equal k times by 2, 2 minus 4. And hopefully you can quite easily see that we've multiplied the 2 in the second row to give us 6, by 3 to give us the 6, okay? In which case, we do the same with all the other numbers. So in the first row, we've got 2 again. We multiply that by 3, so a must equal 6. And in the final row, we've got a minus 4. If we multiply that by 3, we get minus 12, in which case c is minus 12. All right, more often than not, we want to prove that they're parallel. We start with the 2 vectors, and then we find the number k that connects the 2 to show that they are both parallel. And we do this to help us with collinearity, okay? So this is hopefully a diagram that kind of explains collinearity. You've kind of already touched on it in terms of straight line, but in vectors it's a slight bit more complicated. But the idea is that they're all in a perfectly straight line, okay? So here A, B, and C are collinear, but X, Y, and Z are not collinear because they're not in a straight line. And quite often when we're dealing with vectors, we're asked to prove, as I say, that 3 points are collinear with one another, okay? The difficult bit from this is kind of the proof at the end. The actual working is not too difficult, okay? But basically what we're trying to do is, what's happened here, if you look at Y and Z, Z has forced kind of the line off at a slight angle, in which case X, Y, and YZ aren't parallel. But over on the left-hand side, A, B, and C, the 2 lines, A, B, and BC, are parallel, okay? Right, that's not quite enough to prove that they're collinear, because if we had AB as is, and then we had another line, let's call this EF, and say that was parallel, okay, it's not quite enough to say that AB and EF are parallel and thus they're collinear, because they're not in a perfectly straight line. Okay, they may be parallel, but doesn't mean they're necessarily collinear. So what we do is basically use the fact that we've got one common point throughout. So if we find the gradient or the fact that the line AB and the line BC are parallel with one another, the fact that we've used B in both of those lines tells us, therefore, that they must be collinear. And you've basically got to get that point across in your answer to your question. And it can be quite complicated to write. Okay, so if the two vectors have a shared point along with being parallel, then they must be collinear. And this is what we're trying to prove in these questions. Okay, so we've got 3 points, A, B, and C. And we're trying to show, first of all, that they're collinear. And then we're going to find the ratio in which B divides AC. So what we basically want to do, it might help by drawing a diagram. I don't know if I'm doing that first of all, but we're basically trying to show that they're in a perfectly straight line. And if we can find the vector AB and then the vector BC and prove that there's a kind of scalar between them, in other words, there's some number that we can times one by to give us the other, and we've used B as a common point, then we're showing that they're collinear. So the best place to start here is to find the vector AB, which is B minus A. Make sure you get your points right, make sure you get your negatives right, in which case AB is 1 minus 3, 3. So leave that aside for 1 second and then find the vector BC. Some people try and find AC. There's nothing wrong with doing that. And then it just becomes, it means that A is the common point. And it will give us a longer line, which might make it easier to find the scalar. But I'm going to go ahead and find BC, which is just C minus B. Again, make sure you're picking the right points. Take your time with this. Okay, there's a lot of numbers there, so make sure you pick the right ones and make sure you do it correctly. Right, at a glance, you can hopefully see exactly what's happening here. But the idea is that AB is half of BC. So each of those components in AB is half of the ones in BC. You could very well say that BC is 2 times by AB. Okay, and this is what I mean by there's a number that connects them. So there's a number that we can times AB by to give us BC, and likewise, there's a number that we can times BC by to give us AB. Okay, and it obviously will just be the inverse, but we'll come to that later. So because we've now realized this, and we have to have written this first of all, we have to write this number first of all, we can then say AB and BC are parallel. That's not enough to show that they're collinear. So we have to say, and since B is a common point, A, B, and C are collinear. It's a bit of a faff, but it's the same sentence every time. Obviously, it might be different letters and different numbers, but it's the same thing every single time. So you have to write this kind of this number here. You have to have obtained the number first of all. So AB is equal to half base BC, 3/4 of BC, 5 BC, whatever it is. You have to show that number first of all, and in which case, therefore, that tells us that AB and BC are parallel. You can write that out in full or just write the symbol. And then since B is a common point, A, B, and C are collinear. A bit of a faff, but it'll get you a nice few marks. Okay, so for part B, this is where I've drawn it out. It might help you to do this. And the idea is that from these numbers, hopefully we can see that if AB is half of BC, then B must divide AC in the ratio 1 to 2. So AB we can see is 1 minus 3, 3. In other words, there's one part on between A and B, and then there's two equivalent parts on BC. Okay, so that's an AB, and basically that's an AB, and that's an AB as well. So there's 2 of them between BC, there's 1 of them between A and B, in which case B divides AC in the ratio 1 to 2. Okay, so I'll just tuck this on the end of this. The zero vector comes up every now and again. It's especially going to come up when you deal with mechanics, if any of you go on to do that. It's quite a useful vector to be able to find, okay? But what you basically have is a situation like this. You have a bunch of vectors, and when you combine them together, if you get 0, then it's a zero vector. And this is more commonly known as equilibrium, okay, in which case the system of vectors, all of them acting together in one, are in equilibrium. Okay, so the forces acting on it is 0. So it's kind of like the example I often use, and you see in a kind of a past paper, is if 3 things are pulling something in different directions, but that thing stays in the same place. There's forces acting on that thing. So imagine a football, 3 kids trying to pull a football away from each other, but the football actually stays dead still, okay? There's forces acting on that ball, but because it stays dead still, it's in equilibrium, okay? And we can use a zero vector kind of to help us with calculations around that, and that's what we're doing here. 3 forces measured in newtons are acting on a point, okay, point in the middle, as shown in the diagram opposite. If the point is stationary, in other words, in equilibrium, calculate A, B, and C. So we basically have to take these numbers and find this third vector, f of 3, by knowing that they're stationary. And by knowing that they're stationary, we know that the sum of them all must equal 0. Okay, in which case f1, f2, and f3 all add to give us 0, in which case minus 6 minus 4, 2, add the 325, add whatever the hell f3 is, will equal 0. And then this just becomes basically an equation, okay? Because we can say that minus 6 plus 3, which is minus 3, plus whatever a is, must equal 0. And then likewise with the next two rows. And then it's just a case of solving each one individually. A is going to have to equal 3, B is going to have to equal 2, and C is going to have to equal minus 7, okay? If you are asked to find the values of A, B, and C as we are, we can leave it like that. If you're asked to write it as a vector, then make sure you do.